This is just a quick reminder that you should feel free to pause the video if you ever feel you want more time to think and write. Welcome to section 5.32. Good to see you. Have a seat. Let's get started. 5.32, logarithmic functions and graphs. And so, just as a reminder of what we did yesterday, 2 to the x is equal to 64. We translate that into log of base 2 is equal to 64 is equal to x. It had a log of base 2. That's what the base is over here in the original exponential equation. The base was 2. Here, the base was 3. And so we said the 3 to the x equals 81. You could take the log base 3 of 81. That would equal to x. X is the exponent. 81 is the power. But 3 was the base. Log of base 3. Well, here, today we're going to talk about something called natural logarithms. And natural logarithms are logs of base e. Now, you might remember e from our discussion a couple sections ago. E is just a number. E is just 2.7, 1828, 1828, 4. It just keeps on going. It doesn't repeat. It's an irrational number, just like pi. Pi doesn't repeat. The digits are different all the time. It's unpredictable. But just like pi, it's incredibly important for the applications that it has. Pi is used a ton in geometry, and e is used a lot in pre-calculus when you have to deal with exponential functions and growths. You're going to see it a ton in calculus also. And natural logarithms are actually so important that we get our own little convention here. ln of x means log base e of x. Eventually, I suppose people got tired of writing 4 characters here, log of base e, and they just decided to write ln of x. Now you might say, Bergman, the natural log is ln. Isn't that backwards? Well, you remember in Romantic languages like French and Italian and Latin and Spanish, the adjective comes first. So it's a logarithm. And what kind of logarithm is it? It's a natural logarithm. And so the L and the N would come in that order if you were speaking French. So French people, for example, would say the logarithm naturel, the ln of x. And there it is. So that's what ln of x means. You can type that into Desmos and it will know that it's the log of base e. So let's convert to logarithmic notation. What that means is here the base is e, the exponent is 3, and the power is x. The base is e, the exponent is 3, and the power is x. Remember, log of base e is just natural log of x equals 3. Here, natural log of x is equal to 100. So the log of base e is here. The exponent is 100. The power is 100. The exponent is x. So the power is 100, and you get natural log of 100 is equal to x. So if you wanted to solve this equation, you could type in natural log of 100, and you'd get the answer, x. If you want to know what the exponent is, you have to use a log. Here, you might recognize this as something that you can memorize. E to the 0 is equal to 1. E to anything to the 0, any positive number to the 0 is going to equal 1. So switching these around, the exponent goes over here, the 1 goes over here, and you get the natural log of 1 is equal to 0. What would the exponent need to be in order to create a what would the exponent need to be in order to make a power of 1? Well, the exponent would have to be 0. And so what is the exponent? It is 0. Moving right along, e to the first power. So what is the exponent? What is the exponent when you take the log of, when you have as base e, natural log of 2.7, 1828, 1828, 4, and it keeps on going? Well, the natural log of all of this, the natural log of e is equal to 1. You can type any of these into your calculator and you should be able to get an answer. In fact, what I'd like to do is for each evaluate with a calculator and convert each to exponential notation to verify that what's going on is true. I'm going to solve these in 2 different ways. You might ask, Bergman, what is the natural log of 645,778? That would be very much like asking you, when the base is e, what is the exponent? In order to produce a very large number like 645,778. Well, I'll tell you what it would need to be. The exponent would have to be 13.3782. And the way you get that, the way you use a calculator, is you go this method, and you say x is going to equal, you type all this into a calculator, you hit enter, and it gives you the value of x, 13.3782. You can interpret that as being the necessary exponent for putting this here. E to all of this number will give you what you're looking for. It will give you this power. So I want you to do the same thing here. I would like you to type all this into a calculator and say, what is x equal to? X is equal to something. And you can verify that with a calculator, and it'll be the same number. E to the what will give you this very small power. Here, you might notice that the natural log of -5 is undefined. And if you type it in, you'll get an error. Most calculators will just give an error or say undefined, or just break and smoke will be coming out the back. This is what happens when you don't get an answer. Well, now, why is that? It's because if you translate this, you remember the base of the natural log is e, the exponent is over here, and the power is -5. There's no solution to this equation. You might ask yourself, what exponent do you need in order to get a -5? Well, you can't get a -5. The graph of an exponential function doesn't go down that far. It tries to get close to the x-axis at the very best it can do, but it'll never cross the x-axis, and this function will never equal negative value. So you can say that there is no solution to this equation. And here you can say that when you type this in, it is an undefined value. What about here? X is equal to the natural log of e. If you type this into a calculator, natural log of e, you should get exactly equal to 1. Now, why is that? It's because you're asking yourself, what is the exponent when the base is e and the power is e? What is the exponent when the base is e and the power is e? Well, it'd have to be 1, because e to the 1 would equal e. So that's why that is true. Here, if you were to type the natural log of 1 into a calculator, it would give you equal to 0. Why is that? It's because e to the what power will give you e to the what exponent will give you a power of 1. And the answer is, well, you have to have a 0 here. E to the 0 will equal 1, and that's why x is equal to 0. Now we've got something called the change of base formula. And what you've got to be able to do in order to use the change of base formula, you need to the goal for the change of base formula is to allow you to change bases. Let's say you wanted to find each using common logs. If you log base 5 to the 8, some calculators aren't able to do this. In fact, I don't think the iPhone built-in calculator can. Maybe if you turn it sideways, you might see something. But actually, changing the base is often something you want to be able to do. So the formula says if you've got some weird, funky base, then just put it in the denominator of a fraction and use the base that you want. So log of base 5 log 5 goes in the basement. This is just going to be log of base 10. Log of base 10 is very easily common, well documented, and easy to type out on a calculator. So you can say that this is log of 8. The 8 stays. It's just the log of 5 goes down. Log of 8 over log 5 is equal to 1.29. And you can even check that. 5, if the base is 5, here, you see the original, if the base is 5, and the power is 8, the exponent has got to be about 1.29. And yeah, it does check out. Here, common log would mean that this 100 stays in the numerator, this 4 goes in the denominator. Log of 100 divided by log of 4 would be 3.32. And if you wanted to check it, you could see, if the base is 4 and the exponent is 3.32, then the power is going to be 100. log of base 2 to the 32. Log of base 2 is a really popular, the base 2 is really popular, especially when you're talking about computers, because it lives and breathes on its ability to calculate zeros and ones really fast. So it needs log of base 2 often. Anyway, log of base 2, the 2 goes down here, the log of 32 goes here, and you hit enter, and it gives you exactly 5. How can you check that? We can say 2 is the base, 5 is the exponent, and 32 is the power. And yeah, that equation does check out. If you want to find the log of base 3 of 81, then you could use the change of base formula to figure that out. Log of 81, log of 3 is 4. And yep, 3 to the 4th does equal 81. So if all of these examples here were done using base 10 eventually. You can see this is log of base 10. And log of base 10 is found on lots of calculators. But so is natural logs, and you actually didn't need to use the base 10. You could convert to base e if you wanted to evaluate the log of 8, the natural log of 8 over the natural log of 5. 8 and 5. 104, 32 and 2. The natural log of 32 over the natural log of 2. What you're doing is you're changing the base, and so therefore you're making it easier to type into a calculator if you wanted to. Anyway, you get the exact same numbers. What this demonstrates is that it doesn't matter what base you have, whether you choose base 10 or you choose base e, you're still going to get the same answer. Pretty cool. So start assignment 5C2, do the first problem, copy the problem list, and I'll see you in class.